Hey everybody, we are back with Unit 8.2, which I am considering or calling equilibrium constant calculations. Now, this video isn't going to go over every single possible type of calculation, but I'm going to go over kind of the basics, and if you find yourself having questions, just let me know. So when we talk about our equilibrium constant, we talked about how that was a ratio of products over reactants. So it's the products raised to the power of their particular coefficient. Remember that we leave out pure solids and pure liquids from our equilibrium expression, and then we just do some calculations for it. Now, there are a number of ways that you are going to have to use that equilibrium constant in calculations, but for today, we are going to be talking about kind of the basic algebraic parts of that, and that is going to be how do I, if I have concentrations, figure out what the K value is, or if I know the K and most of my concentrations, what can I find for this missing piece? And then if we do some manipulation to the reaction, how does that affect the K value? So like I said, just as a review, our K expression is that ratio of products over reactants raised to the power. And so anytime we do any problem, we need to always write that K expression first before we can kind of go through and do anything else with it. So we're going to get a little practice with this right away, and then we'll see what's going on. So this first example, example 1, says that nitrogen reacts with hydrogen to give ammonia. And I'll get you that balanced equation in just a minute. And it says an equilibrium mixture, so at equilibrium at 400 degrees Celsius, was found to contain 0.45 moles of nitrogen, 0.63 moles of hydrogen, and 0.24 moles of ammonia per liter. Calculate the equilibrium constant for the system. So we are trying to actually find the K value with the values that are given here. And so I'm going to work through this example with you to start off with. So we've got our problem from before, and we're kind of diving right into examples because honestly, that's the easiest way to do this. So the first thing you need to have is your balanced equation. And so we have nitrogen reacting with hydrogen, N2 plus H2, and that is, just want to make sure my focus is good here. Yep, that's off. Come on. All right, sorry about that. It's going to be N2 plus H2, and then that is in equilibrium with ammonia, which is NH3. So we've got to balance this equation out first, and to do that, our N's, we're going to need 2 N's, and that means we end up having 6 hydrogens, so I'm going to need a coefficient of 3 here. So when you think about calculating a KEQ value, the first thing you need to do is you need to have the equilibrium expression. Now, in this case, all of these are going to be gaseous, so we're going to have gases for all of these, and they would have to specify that, and I'm telling you right now that they're all gases. So in this problem, if we want to write our KEQ expression, which a lot of times gets you, honestly, 1 point on the AP exam, what we're going to do is we're going to do our products over our reactants. Now, since this is giving it to me in moles here instead of like an atmosphere unit, then I know that I'm going to be calculating a Kc value, which is an equilibrium concentration constant, or we can just call it our KEQ. If it were given to me in pressure units, we'd want to call that a Kp, and it'd be a little bit different. So it is the concentration of the ammonia squared, because of the coefficient of 2, divided by the concentration of N2 times the concentration of our hydrogen to the 3rd power. So in this case, because it's kind of a very basic problem, it tells us how much we have of our nitrogen, how much we have of our hydrogen, and how much we have of our ammonia. And it tells us it's per liter. So that means in 1 liter, then we have those concentrations. These here, remember, are moles per liter unless specified. So in this case, we don't have to do any division because it's in a 1 liter container because it's per liter. If it were multiple container or a multi-liter container, you'd have to do a little bit of math before that. So what I get to do now is I just get to put my numbers into my expression here. So it's going to be 0.24 is my concentration for my ammonia, and that's squared. So what I'll do is I'll put that concentration in and square it. And then it's going to be 0.45 in the denominator for my concentration of my N2. And then my concentration of my H2 is 0.63, and I'm going to cube that. Now, you might ask yourself why I don't have units in here, because we're talking about molarity. Equilibrium constants, they are kind of a unitless entity, and so the units aren't super important. So it's going to seem a little weird, but you'll have kind of unitless things go in, and then a unit pops out at the end. And it's not something you have to be super worried about keeping track of like you would a K value for, let's say, a rate constant. So all I've got to do is then put this into my calculator and solve it out. So I'm going to get a K value after I do that of 0.512. Now, just as a refresher for us, a K value that's less than 1 means that this is a reactant-favored process. So at 400 degrees, it means that our equilibrium lies where I have more reactant and less product. Okay, so if we talk about product-favored or reactant-favored, this is definitely a reactant-favored process. And if you look at it, you can kind of see I've got higher concentrations of my reactant than I do my product. So what you could potentially also do, and we're not going to do an example, but I want you to be aware of, is that I could give you this K value here, and then I could give you an X, like maybe we put this in as X, and then you'd have to solve for the concentration at equilibrium. So that is something else we could do. It is very kind of basic algebra. I'm not going to go over that. We'll go over examples in class together, but just be aware that that is something that could happen. All right, so that is equilibrium calculations for K. Legitimately, it is just that easy. There's really not that much kind of stuff going on with the K yet. We will get to a point where we start off, or we'll get to more complicated math, but right now, that's about it. Now, what happens sometimes is you will actually make changes to a chemical reaction as far as the coefficients go. And when that happens, you will actually change the K value for your reaction. So it's kind of along the lines of the party trick, which we don't always love, but it is something they could ask us on the exam. So if you take a look at an equation, and the coefficients in your original balanced equation that you have a K value for are multiplied by some factor, so like 2, 3, 4, whatever it is. Whatever that multiplier is, that is what you are going to raise your K value to calculate your new K. So if you multiply your reaction coefficients by 3, a la Hess's law, your K value gets raised to the third power this time. Okay. If you write the equilibrium expression for the reverse reaction, so let's say you know the K, but you have the reversed reaction, the K value is going to be the inverse or the reciprocal for the forward reaction. So you essentially take it to the -1 power, and then you can find that K value. And then I guess on the top of the party tricks there, if you add 2 or more reactions, a la Hess's law, the new equilibrium constant is going to be the product for those 2 things. So if I have 2 equations that can kind of join together, like a Hess's law problem would, and I want to figure out their new K value, if I have both K values from the original ones, I'm going to multiply those. I will show you what that looks like in just a second. So our example number 2 here is going to be, excuse me, my original equation is half I2 plus half Cl2 turns into ICl. And for that, my K value is 4.54 times 10 to the second. So it's product favored at this point. The question is, what would the K value be for the following reactions? A, it's 2I, 2Cl, and 4 ICLs. And the other one, it's ICl turning into half I2 and half Cl2. So we've got kind of 2 situations that we'll take a look at. And then our third example, and I'm just going to go through these first, and then we'll actually work through them, is a combining equation situation. So we'll talk about all of these in our examples, and then give you a chance to try it out on your own. Okay. So here are our first 2 examples with example 2. So again, this is our equation, and this is the K value that corresponds to this temperature and this particular reaction. So if you think about my K value is going to be the concentration of ICl divided by concentration of I2 to the half power times the concentration of Cl to the half power. So when I normally do this, this would be my K expression, and that is equal to this value here. But if I change my powers or my coefficients here, that changes the powers in here as well. So if I change this to a squared instead and a 4, what ends up happening is that my K value is getting raised to the 4th power. So if I know what's happening in this case and my whole reaction is being multiplied by a coefficient of 4, my K value, 4.54 times 10 to the second, is going to be raised to the 4th power, and that's how we're going to see that change. So in this case, it's going to end up being 4.25 times 10 to the 10th, okay? So it magnifies because our coefficients turn into these superscripts here, and then it ends up being a bigger number. So I want to see if you can figure out what we got to do with this one here. Okay, compared to our original. And if you look in this case, it is the reverse reaction. So this is our forward reaction right now, and now we're looking at our reverse reaction. So if we have a reaction that's flipped, then what we're going to do is we are going to take that to the -1 power, or the inverse or reciprocal or whatever you want to say. So my K value for this process is going to be that 4.54 times 10 to the second value, but now I'm going to take that to the -1 power because I'm flipping it. So in this case, it is going to be 2.2 times 10 to the -3rd. And if you think about it, if I have a very product favored equilibrium for my forward reaction, the reverse should be a reactant favored value. Now, in theory, you could have a bunch of things happen. So you could have an inverse and a power happen. And if that happens, you just treat it kind of the same. So you would, take it to the 4th power and then invert it, or whatever is required of it. So it just kind of depends on the scenario. I've seen this on multiple choice questions a lot, where they want you to manipulate K and see what's going to happen. Again, party trick in my opinion, but that's all right. I don't write the test. Now, the last one on here, it says calculate the K value for the reaction using the following information. So this is very much like a Hess's law problem. I have this equation here that I want to solve for. So I want 2NO plus Br, and that turns into 2NO-Br. Here are the two equations I'm given, and then here are the two K values for those equations. So if I look at this and kind of break it in half like we do with a Hess's law, I have an N2 on both sides and an O2 on both sides that can go away. And when I do that, I'm left with the equation that I'm trying to make. So that works out really slick. Nothing crazy manipulation-wise you have to do here. But if I want to find the K for this overall process, I need to multiply these two K values together. So I'm going to take 1 times 10 to the 30th times 2 times 10 to the -27th. Because if I put those two processes together and multiply their Ks, I'm going to get those values. If you think about the math behind this, essentially what's happening is these expressions are canceling each other out when we multiply them as well. And I can go through that math in class if you want me to, but you can also just trust me. So when I do this multiplication, it ends up being 2 times 10 to the 3rd. So when I have these two processes together, even though this one is very much not product favored, this one is very product favored. And when I couple those two things together, I still get a product favored process. Okay, so that's kind of it for this. Kind of short, kind of sweet, kind of easy. It will escalate from here. So just be aware. If you have any questions, please get them cleared up. Otherwise, good luck.